Good morning everyone, my name is Yeding Li, from the University of Chinese Academy of Sciences. It is my pleasure to give a presentation here. The presentation I am going to do today is FlashSchema, achieving high-quality XML schemas with powerful inference algorithms and large-scale schema data. Good morning everyone, my name is Yeding Li, from the University of Chinese Academy of Sciences. It is my pleasure to give a presentation here. The presentation I am going to do today is FlashSchema, achieving high-quality XML schemas with powerful inference algorithms and large-scale schema data. Firstly, let me introduce XML schemas. As a main data exchange format, XML has been widely used in various applications on the web. XML schemas have always played a crucial role in XML data management. Obtaining high-quality schemas to avoid or reduce application risks is an important problem in practice. Many XML documents in practice are not accompanied by a valid schema, thus making schema inference an essential task. The XML schema inference is divided into two important parts. Inference of regular expressions, REs, is an essential issue in the XML schema inference problem. Besides re-inference, type inference is also an important aspect of XML schema inference. Presently, the most powerful model for XML is the k-occurrence regular expression, KOR, which means each symbol can occur at most k times in an expression. However, it does not support the unordered operator interleaving, whereas this operator plays a contributing role in RNG, making its coverage only 76.11% in RNG. This indicates the need for the interleaving operator, and a more powerful model than KOR. Type inference is also an important aspect of XML schema inference. Unfortunately, most of the existing approaches either do not take into account type inference, or omit the types and consider all values as strings. Well, let's move on the previous work part. Presently, in the literature, there have been only a few attempts to address either KORs or interleaving. Currently there is only one paper addressing KORs with limited interleaving. Further, almost all XML inference algorithms only support learning from positive samples. It has been proved that learning from positive and negative samples is more powerful than only from positive samples. Therefore, we aim to learn from both positive and negative samples. To our knowledge, only two methods can infer simple types only by a pattern matching process on the format of the values. The characteristics that make unique a type, which is called the lexical space according to the W3C recommendation. Let's move to the our work part. We develop a tool FlashSchema for high-quality schema design based on several powerful yet efficient schema inference algorithms and large-scale schema data. Specifically, it supports interactive schema design and schema recommendation, which cannot be supported by existing tools. In order to solve the k-occurrence and interleaving problem, we propose a new subclass of REs, k-occurrence REs with interleaving, KWARs. It covers almost 100% DTD, XSD, and RNG schemas. We devise powerful and efficient algorithms to infer KWARs from both positive and negative samples, which also form the basis of interactive schema design. In addition to that, we provide a new solution for type inference, which overcomes the limitations of existing methods by using word embedding techniques to take the semantics of the context into consideration. We also propose schema recommendation for schema design, which is suited for situations where the users only know some elements of the schema under design, or the users do not want to design from scratch. Now, I want to illustrate our main algorithm. The algorithm can be broken down into 4 steps. Firstly, from several XML files, we extract multiple groups of samples. Then, each group of samples is fed into a KOA synthesizer to produce a corresponding deterministic KOA. Next, we mark the synthesized deterministic KOAs and generate possible REs from the marked KOAs. By using an regenerator, we convert the generated REs to the corresponding content models and get the data types corresponding to the content models, based on the lexical space analysis and the semantics of the context. Finally, we combine content models and corresponding data types into an XML schema. Okay, I want to use some examples to illustrate our framework FlashSchema. How does it work? FlashSchema gives 3 application scenarios for different requirements. They are 1-pass schema design, interactive schema design and schema recommendation respectively. Here is an example of inferring an RNG content model. Suppose we extract positive samples negative from XML files. Then, we execute the KOA synthesizing algorithm to produce a 2OA and mark the synthesized 2OA. Figure C gives an intermediate SOA. The final we extract is R. We convert R into an RNG content model. The inferred RNG content model is shown in Figure 1. Since the data types of RNG are not as rich as those of XSD, we next see an example of inferring XSD data types. First we embed the inferred RE and the REs in our library into vectors by using the CBO model. Then, we find the most similar regular expression by vector similarity computation, and return the corresponding types. Our method can also be applied to other type inferences, such as RDF. The resulting schema may be unsatisfactory when the samples in the user's hand are not sufficient. Let us look at an example that illustrates the process of interacting with users. As shown in Figure 2. Firstly, FlashSchema returns the resulting schema. Suppose the user is not satisfied with the resulting schema, because she does not want the element A to appear more than twice. So the user constructs a negative XML file. Then, FlashSchema return a new schema based on the new input. The user finds that the new resulting schema is consistent with her intention. The interactive process stops. We have collected 532,230 XML schema files from the real world and built the largest XML schema library so far through a series of processing. We can return the most practical schemas in reality through schema rank, which contain the XML elements that the user provides to Arthuli. These widely used schemas in reality have been tested by practice, and hence are of great value to non-expert users who have limited knowledge on XML. And even to experts who do not wish to design schemas from scratch. Finally, let's look at the experimental efficiency of FlashSchema. We use two publicly available datasets, InCollection and www, as XML inference sources. InCollection is a collection of 45,985 books, with an alphabet of size 14, and www is the large dataset, containing 2,226 URLs with an alphabet of size 10. The experiments are conducted on the large dataset www. The results displayed in Table 1. It is noteworthy that FlashSchema can finish the task within a few seconds. The results shows that two datasets share similar trends with only slight differences. FlashSchema strikes the best balance between preciseness and conciseness. The reason why our FlashSchema achieves such good results, especially in inferring RNGs, is due to its unrestricted support of interleaving. So that's what we did. Thanks for your attention.